Okay, what I'm going to try to do is I'm going to try to solve a very, very small example with VQLS by hand using Quirk of a really simple system of equations that we can do so that we can do it with 1 qubit. So I'm going to try to see if that helps me. So the idea that I had was to do, what about we do x plus y equals 4 and x minus y equals 0, right? So the obvious solution for this system is where x equals 2 and y equals 2, right? I hope so. Yeah. And so in this case, I guess A would be 1, 1, 1 minus 1. And that's awfully close to some quantum gate, I think. Is it the Hadamard gate? And the Hadamard has like should be still normalized. B would be 4, 0, right? Or 4 times 1, 0. And that is actually 4 times the ket 0, right? And that is x, right? So that's what we want to approximate x for. But the truth is, the algorithm is going to give us an x that it's not directly this. It's going to give us an x that's normalized. So it's going to give us an x that is going to give us these. So then we'll have to figure out. So it's going to give us these. Okay, let's hear it. But for these, because the thing is, we can use a much more simpler ansatz for these. And what I want to test is I want to test whether you can just use the Hadamard overlap to solve these. And I know that it might not work. I don't know. Let's see. Okay, let's try to see if this works, because the way that I do this, the way that I approach this problem is, as I said, right. So we want to calculate these as this being our ansatz, and we want to make sure that this is overlapping with these. And so here, because we just need 1 qubit, right? Because A is like that, but we need to decompose A, because that is not. Can I check unitary matrix checker or something like this? Unitary matrix calculator. It's probably not unitary. Interesting. Whatever. Let me see. Just what I want to check. I wanted to check one thing, and I forgot. I wanted to check. Oh yeah, the quantum gates. So quantum gates. Wikipedia. Quantum logic gates. Okay, let's see. Look at this. So, in theory, so if I take these and I add it to these, I actually get what I want, don't I? Yeah. Yeah, because it's all ones. So, okay, so that turns out to be easy as well. Okay, so actually A is x plus z. Okay, so this means we kind of have to do this twice, right? Like we have to do this one for this portion of A, and one for this portion of A, and then add up the stuff, right? I think that's the way this is supposed to work. I mean, I don't know how the post processing is going to look like afterwards. I haven't really checked it, or I did check, but I don't remember. Okay, so this means this is A, and so let's go to Quirk. So really simple. I mean, we only need one qubit for these, obviously. And so I think a one parametrized rotation here, and just start with pi, or let's just start with something like, just start with 0. So there's no rotation. So this is our ansatz. Okay. Then what we want to do, remember, is we want to do so this is the ansatz. We want to multiply by a, but not a like the whatever component of a first. We're first doing the x. So this just means x, right? And now in the second qubit, what I want to be doing here is I want to be you know, preparing a state that represents b. So I can do a Hadamard test, an overlap test. Now, how do I prepare B when B is not unitary, obviously? Because B is these. It says 4 times these. That's what bothers me, is how can I get rid of these? Because that's probably the reason using a cost function like this one helps, because you can get rid of you kind of can get rid of but to be honest, if I would just, because this is literally 4 times, like as we said, this is 4 times 0, right? I know that seems too simple. So it's just the identity. So I'm doing nothing. Destroys the universe. So I'm doing nothing, right? Or just the identity. And now I'm supposed to. So now I want to do the Hadamard test, which was basically a control knot like these, and then checking the chance display. And so this will be 0, because the way the Hadamard overlap test works is you kind of get these, so you do this plus this minus that. So that's the way the Hadamard test works. 0, and 0 means they're totally different. We want this to be 1, right? So we want to, yeah, you can see here that they are completely orthogonal, the states. So that's why you're getting these. So, and and the idea is you start with this random, I mean, I don't know, 0.5, whatever. Oh, sorry, it's probably 0.5. And now things start moving, right? So, so this is no longer 0. This is no longer 0. There's a little bit of these 2 components in here. But my guess is if I do pi, then, or pi divided by 2. Okay, so now it's 1. So this means it means that, so what this is telling me is that this ansatz is a perfect solution, because it's a perfect overlap. It just feels too simple. It's too small scale that it just feels uncomfortable. An Ry rotation of pi gives me, what state it gives me? It gives me the state 0, 1, which is basically, sorry, wrong. It gives me the state 1. Yeah, yeah, but that's correct, right? I mean, that's kind of so that's what we. Oh no, but it's not. It's not correct. Because we because b was 0, right? Mm. What am I doing wrong? Oh, wait a second. This is just the X part of the whole thing. Okay, so maybe I should be taking some notes, you know. I need a note-taking app somehow. I don't want to use Paint for these, but I can probably use Paint inside and kind of, you know, take some notes in here. Oh, beautiful. Oh, but I can't. Yeah, I can take notes in here actually. Oh, come on. So, for the X part, because remember A is X plus Z. So for the X part, like we're getting a we are getting a solution of what am I doing? What am I doing? First of all, am I doing something stupid? Because I need at the end to do that to kind of sum up the whole thing, right? Yeah, this is the other control cost function. Sum up things. Mm. It gives me 100% 1. Okay, let's just move on. And so this gives me like 100% 1. And for the Z case, so if I change this with the Z gate and I go back to 0, right? Now I get, okay, so now it's kind of correct, right? If I get like, because if I do pi, it's going to be 0. We want the parameter to be, we want the parameter, so now it's a perfect overlap. So it's 100% 0. Okay, I think so. This is 100%. Sorry. So it's 100% 0. Well, and now if I add them all, it should be like the cat 1 plus the cat 0. I don't know if this is the right thing to do. As in like that's the solution. Which basically it's like normalizing. So this is literally these, right? But like I mean, they should be normalized, shouldn't it? And so this is probably a whole mess, what I'm doing right now. So what am I trying to do? So it's one, one. And so what this is telling me is that so A times this, which is the plus state, right? it's not equal. It's not equal to B definitely, but it's so because B has got the 4. So B was like 4 times 0, right? So B was like 4, 0. Because that's the problem. I don't know what to do with these constants. I don't know what to do with these constants. If we do, let's do these. So this is a small matrix, so it shouldn't be a big deal to do these. I don't know what I should do with this with this kind of normalized or not normalized or whatever. If I do these, right? This basically gives me 2, and so this gives me 2, and this gives me basically 0. So actually, that is proportional to the solution, right? I'm just missing a factor of 2. Proportional. So that was not a bad. But I think my intuition can't be that wrong. My intuition, it just can't be that wrong. Let's recap. What are we doing here? So we're doing these, and so yeah. I mean, I kind of I basically did the optimization kind of but just by trial and error. So I just tried 2 values, 0 and pi, and here the optimization should work differently. And now the whole point of this algorithm is not just whether intuitively this works or not, because these as a cost function might not be optimal for an optimizer, right? So it might still not be taking us down the right gradient, down the right slope to minimize whatever. So this, I don't even know what I'm doing these then. But what should I? So what do I do with those? What I don't know is what do I do with those coefficients? What can I do with those coefficients? Because I can't just prepare B like that, right? And X should be normalized. So the truth is that if I do stick to these, can I just so I do stick to this like convention. Where's my here? So the matrix is like these. So this is like that, right? And if I multiply that, it's basically these and 0, right? And in theory, this is where is that? So in theory, this is equal to these, correct? So, so this would be then equal to these, right? Which kind of I can see that if my original vector is these 4, 0, and I want to normalize it, then I should do these, right? I should divide it by the square root of the norm. So I should divide it by 16, right? Should I? But still, that doesn't. So let me check quickly. So 1 second, let's take a look at the time. What time is it? Okay, cool. So if I do these, so divided by 16, it's kind of then still 1/4, right? So still would be 1/4. That would still be the normalized thing. But I'm getting, I don't know, something's off with these 4, right? Like, maybe I should normalize that as well. Yeah. So maybe for this to work out, I should actually normalize B. And so I should try to basically implement. Yeah, but that's not a unitary. That's not a valid state, is it? That's not a valid state. How do I know what B, like, because the example, so how can I take B in a way that works with the circuit? Now I'm super lost. I feel this is really basic. B. So we're also given a normalized complex vector in the physical form of quantum state B, which can be generated by unitary. I mean, is it just a precondition that those are the only things you can do by unitary operation applied to the ground state of n qubits? So wasn't there a way to turn a convert matrix unitary? Isn't there a quick way to do that? Isn't there a quick way to do that? A unitary transform of a vector. Unitary matrix. I've been searching for this already. N by n. Okay, that doesn't help. Because okay, by definition, that's, so I should just normalize it. But that's what I've done. but it doesn't give me a valid quantum state, does it? No, it doesn't give me a valid quantum state. So how can I use B? How can... So, okay, so I need, should clean that up probably. I need, come on, I need, so I need a U that basically, you know, multiplied like these gives me that, right? So man, I'm so bad at these. A, B, C, and D. So you basically need like, you know, A plus C, right, should be, so AC should be 4, 0. So A is 4 and C 0, right? And then B and D can be kind of whatever they want. But that's like none. That's definitely not something that I can. It's definitely not unitary. I mean, again, it's a Z. Okay, it's a Z gate because I don't care about this stuff. It could be done with a Z gate or with an S gate. I see. Okay, so it could be done actually with a. What am I doing? Come on. It could be done with an S gate. Have I? Was it taking notes of these? Here. So this could be done with, the truth be told, a Z gate, like 4 times a Z gate would work as well, right? Because, so and then I have this coefficient here side, because these times, these basically leaves it like it is. And so with a factor of 4, that's what we get. Okay. But effectively, the identity will do the same. And it's correct. So if we're not doing anything here, yeah, the identity will do the same, right? So that's really what U is. So that's fine. But what do we do? What do I do with this 4? That's my problem. I don't know how to come back. How to kind of then get back to a final solution, right? Because so with X I get 100% 1. With Z I get 100% 0, and so I assume that this is the 1 plus 0 state or 0 plus 1 state, which is the plus state. Which kind of it gives me a solution that's proportional, because it gives me these here. And this is just proportional to that, but how do I know what the proportion is? Because that's definitely something that would need to add to these, which is kind of my X, to then say, hey, here you go, that's a solution, right? Because my solution is 2, 2. And I just found a solution that is, my solution is 2, 2. But I found 1, 1. So, am I just being blind and stupid? Because 2, 2 is the solution, right? Oh yeah, I'm stupid. I was making this from. I think that was the wrong thing. I was not applying this to the right. So 2 is the solution. Um, and so this is what's actually these, right? And so this is the solution. That's crap. That's not what. That's not. Sorry, that's crap. So this is the solution. Yeah. No, this is yeah. So because I know the solution, what I can. Yeah, of course, and that's why I take the 2. Yeah. Ah, come on. It's there. I just did this. I just applied this in the wrong. Okay, so let me can I select everything and get rid of these? So sorry guys, sorry. I hit the wrong button. I hit the wrong button. Now we're back here. Let's recap. I was saying let's recap. So what we have is we have oh, come on. So we've done. I know how this is gonna work. I know how this is gonna work. So again, A is basically x plus z, correct? For x we found the state 1. For z we found the state 0, and so this means that our actual x. Uh, it's not x. I mean, this is really not x yet, but like something that's proportional to x. So our solution is basically like 1 plus 0, right? So this means that our kind of state in here is, if we normalize it, right? This. Sorry. So if I do and if I basically do uh, a times these, then I get what do I get? So I actually get these. Do I? So it's kind of proportional to some extent. Is it? Yeah. Well, like you get like these. Yeah. Yeah, kind of. So it's proportional by these, right? Um, right, because if A is like 1, 1, 1 minus 1, yeah. Yeah, exactly. So now this is not really like our x, right? Because remember, this is equal to these divided by the norm. That's what the tutorial here tells us as well. Here we go. So here you go. Now here, so if I know that, no, I know my solution. I know x is 2, 2, right? So the norm of these is the square root of 2 squared plus 2 squared, which is basically square root of 8, which is basically 2 square root of 2. And so so this is basically 2 divided by 2 square root of 2, 2 divided by 2 square root of 2. The 2's cancel out, and actually, yeah, I get actually exactly that. Yeah, which is basically what I found. So that is correct. That matches. So that works, right? Now the question is whether this is good enough for for a gradient algorithm or gradient optimization to work or not. That works. That allows us to find the simple Hadamard overlap test allows us to find that exactly. Um, and what happened with the coefficients? The coefficients are just gone, right? Like what did I do with them? Nothing really. So it was x plus z. It was x plus z what I did, right? x plus z, basically the two different circuits. And that's really it, because for me, like B, right, I did nothing because B is just B. It's B is just 4, 0, right? B is just 4, 0. So it's kind of like 4 times 1, 0. But am I able to solve for these if I don't know? So if I, let me see, if I select everything, just I want to select everything. And so if I have, so the solution that I find is this one, right? And I know that this is actually, and I know that this is actually, is proportional. So there must be like kind of AA in here, right? Not AA. So this is proportional. I'll call it like P. Is proportional to these, right? So P squared squared plus P squared squared, right? So those basically things, okay, so these things cancel out and get it like P2s. So sorry, so this is like I got P squared divided by 2 plus P squared divided by 2. But this in turn kind of is equivalent to say P, like all these, so I think I can do that, right? I hope my maths are not that rusty. Which basically means that this is P divided by square root of 2 plus P divided by square root of 2. So 2 times P divided square root of 2. Yeah. So I have like that 1 is equal to square root of 2 P times, and this thing cancels out, and so I've got basically that. Do those things cancel out? 2P. Have I made a mistake somewhere? What I want P to look like? I want P to be something's not correct in here. I made some mistake. So sorry, that's the bottom part of the whole thing, right? The 2P square root of 2. Yeah. So sorry. So this is P square root of 2 divided by 2P square root of 2. Exactly. So that basically makes it, it's going to be made. I think the way you were doing this, right, was like, so I can flip that and say that's like square root of 2, if my maths are not rusty enough, times P square root of 2. And so that leaves me with like basically 1/2. No, I wanted 2, not a 1/2. What I did, I did something wrong. My maths are a bit rusty. Is this correct? Oh, here I made a mistake. That's not correct. That's a mistake. Okay. Yeah. That's a mistake. That's why I made a mistake. So here you've got Yeah, but I guess you can solve for that somehow, right? So this is where I made a mistake because you cannot just that doesn't work this way. Um, anyway, but you've got like no, but wait a second. You have d, so you actually have 2p squared. So you have like square root of like 2 times d, so square. Okay, so this is p, correct? Yeah, this is p. So this whole thing here then becomes like this whole thing here becomes. Can I just make that bigger? Probably it's going to be easier. So I can move. So this whole thing here becomes basically p. Come on. Yeah, basically p and p cancels out, and so yeah. But I just proved the equality. I just want to find p. What have I done? What have I done? Man, what have I done? Uh, ah, squared. That's correct. So, no, what am I trying to find? So I just proved the equality, but what am I trying to find? Um, oh, come on. Wait a second. So I've got these, and I'm trying to find. No, that's not right. Let me start over. Okay. I know this works, but I wanna prove you that my maths are not that rusty. So we have these, right? And this is supposed to be so okay, these times whatever constant is supposed to be equal to um, it's supposed to be equal to a vector. How do I solve for that? To like um, basically q, right? We know it's the same because we know it's gonna be both the same divided by q squared plus q squared. So 2 times q squared, 2 times q squared, right? So this is like 2 times q squared, 2 times q squared, which basically is q squared root of 2. Yeah, q, right? And so we're just saying that basically QQ equals uh, what, like P times Q squared root of 2 times 1 to the square root of 2, 1, 1. So those things go like that. So I then get, what? What am I doing? Oh, my maths is so rusty. Come on, I'm not going to put myself into shame anymore. How do you solve for that? Come on. No, like seriously. Uh, so you have Please do not subscribe. So I've got like these. I know it's a vector that it's like, I know that it's something QQ, right? And I know that this is like 2 times Q squared, which is basically, I've got like Q divided by 2 times, no, by Q squared of 2 and Q divided by Q squared of 2. And this is, yeah, but this is effectively telling me Q can be whatever. But this must be 1, 1, right? And so, but Q can be whatever. I don't understand that. If I really want to find X, like, I don't understand. Maybe it just works. Okay, whatever. I just probably do something wrong. My math is super rusty, but you get the point, right? So you get the point. We found the right solution with 1 qubit, and yeah, basically. Now, still, that doesn't mean that the. Oh, wait a question. Wait a second. But we know that. That bothers me. That bothers me. We know that we know the 4-0, right? We know the 4-0. Because it's got to be 2-2. I mean, and if we have these as a kind of our intermediate solution, and yeah, that's so, and then you have like 1, 1, 1 minus 1, then that kind of basically takes you to these, and we want these to be like 4-0, right? So this means there's going to be some kind of Q in here. That so something's not correct. No. I don't know. Okay, I said I'll stop. I kind of I found the solution. I'll try to figure it out. I don't want to put myself into shame anymore. But yeah, that's basically. Now the question is whether these is something that works well with an optimizer, right? That's another question. Whether that kind of cost function works well with an optimizer. But it should work well. Come on, it just bothers me so much. Give me a second, okay? All right. What am I doing wrong? I'm feeling so shameful right now at this moment. So we found like our V parameter, like our V alpha thing, like kind of found the state, right? That should be equal to these. Okay, good. So now the question is, what is these, right? So if we have these, we know that this has got to be a vector of elements QQ, because we know it's got to be somewhat proportional, right? And it's going to have basically q, we said square root of 2, right? Because this is, so this would be q, so this would be like square root of q of 2 times q, and so that would basically leave us with square root of 2 times q. So yeah, so that's this here. So I can take that part over here, but I want to solve for q. I want to know what q is, because if q is, for example, 2 2, right? Uh, because essentially that's telling me that I can say q. Well, yeah, because that's the norm. That's the norm of any vector like that, right? That's just the same. That's why I keep running into circles. So, and how can I basically solve that? I know it's along these lines. I know that it's okay. So I know that it's basically like it's got to be some kind of x, right? And I know that this is the matrix that I have, and this should be okay. So this is the way to solve for that. That's so rusty, man. But it's also not that. No, no. Why? Why? Wait a second, because that should give me this times this. I think okay. So this basically means that this should be okay. So this should be these plus these, right? So it should be 2 times x square root of x square root of 2, and this is 0, should be 4 0. And so this means that 2 times x divided by square root of 2 should be 4. Is that correct? But that's not correct. That's basically, that's just not correct. So what am I making the mistake? Because that would basically mean that x equals like these, and that's not what. No, square root of 2 divided by 2. And if I replace square. Wait, yeah, it's true. Sure, of course. And x equals then um, okay, so then, sorry, then these is the vector we're solving for, and so this is basically square root of 2 divided by 2 divided by square root of 2, which basically goes away, and that's what I do. Yes, I have it. Okay, math cringe has reached the end. Okay, cool. We have it. It works, but now the question is still whether that works well for an optimizer. No, sorry, that was too much of a long video for this stupid mathematical cringe, but it was fun. It was fun, nevertheless. Oh man, I'm rusty. Okay, cool. But I figured it out at the end, so I'm calm. I like that. So it works for 1 qubit. So this is VQLS for 1 qubit with just the Hadamard overlay test as a and so, the idea is you want to minimize that, right? So, okay, the next video is I'm going to try to actually do that in Circ or maybe in Qiskit just, and then try to see if that works as well. Let's see if we can do that. The one qubit example, I'm going to hard code the 1 qubit example, see if that see if that works with the optimizer and it finds the right thing. Okay, so it's going to be the code part. Because then, I mean, then it's just a matter of scaling it. So you've seen what I've done is you decompose A into a set of a sum of unitaries. The coefficients, you use them at the end to really solve for the x, right? So B is something you also turn into. You kind of take the coefficient out, and then you get that state you want to represent. And the coefficient you have to keep it later to actually solve for the x that you want. In this case, we didn't have to have any coefficient in here, so I don't know what would happen. But I'm guessing that you can also take that out, and then at the end you use the coefficients to solve for the actual x. Okay, perfect. So but I was kind of lucky, I guess, that I could turn this into unitary so easily. But I could try to encode that next time. Maybe let's try to code it to like another bigger example. Maybe this 1 qubit example. I don't know, the 1 qubit example. But that's essentially what's doing. And so here in this part, like the whole concept here is a bit different, right? But we'll talk about this in the summary video. So here the cost function is different. So we're not doing the just the overlap test. We're doing the Hadamard overlap test. We're calculating different things that you kind of take out of expanding those equations, and then you just kind of follow the math and do that. But I just wanted to do it once intuitively. Anyway, it was fun.